Okay, let's get into it. We all look at those LLM leaderboards, right? The lists that tell us, Model X is better than Model Y.
Right, and we basically take them as gospel.
We treat them as unshakable truth. But here's the question we're digging into today. What if the test itself is just flawed?
And that's exactly what the BenchMark2 framework is all about. It's forcing us to check the quality of the yardstick, not just the thing being measured.
Yeah, because the sources point out three huge problems that are, lurking just under the surface of these rankings. The first one is pretty obvious.
Ranking inconsistency.
Exactly. You have Model X beating Model Y on benchmark A, but then on B and C, it's the total opposite. You get three different stories from three different tests.
It's chaos. And then the second problem is what they call low discriminative power.
Which basically means the test can't really tell the models apart.
Yeah, precisely. Imagine a test where, like, the best model gets a 90% and the worst gets an 88%.
All the scores are just clustered together. It's useless for comparison.
And then there's the weirdest one, the one that feels like a bug in the matrix.
Rank inconsistent items. This is where bigger, supposedly smarter models, say GPT-4, fails a question.
That its smaller, weaker sibling, like GPT 3.5, actually gets right. It just shouldn't happen.
So how does BenchMark2 even begin to fix this mess? It introduces three new metrics.
It does. It starts with the big picture. Cross-benchmark ranking consistency, or CBRC.
Okay, so what is that checking for?
It's basically seeing if a benchmark's ranking of models agrees with other benchmarks in the same field. You want high agreement, right, something over 0.7 or 70%, to feel confident the results aren't just a fluke.
Got it. So that handles the conflicting stories. But what about that clustering problem you mentioned?
That's where the Discriminability Score, or DS, comes in. It actually measures the score spread.
So make sure there's enough room on the scoreboard to see a real difference between the top and bottom performers.
Exactly. You're looking for a DS score above 0.4. If you have that, you know the test is actually spreading things out in a meaningful way.
All right, now let's get back to that bug in the matrix. The rank inconsistent items. That's tackled by the third metric, right?
That's right. Capability Alignment Deviation, or CAD.
And this one is interesting. It sort of assumes that within the same model family, bigger should mean better.
It does, but it's not circular reasoning. Think of it as a diagnostic tool. We use that known trend that larger models are generally more capable to find the flawed questions.
Oh, I see. So if a question breaks that rule, it's the question that gets flagged, not the model.
Precisely. CAD penalizes those specific items. You're looking for a high CAD score, something above 0.6, to show the test questions are well designed.
And when they applied this whole framework to, 15 real-world benchmarks, the results were kind of alarming.
Oh, definitely. It showed a huge variation in quality. For example, a math benchmark, AME 2024, did great. It had a really high DS and a strong CAD.
So it's good at telling models apart, and its questions are solid.
Exactly. But then you look at something like Psycho, which is for social intelligence,
It's a pretty critical area.
a very critical area. And it was just problematic across the board. The CAD scores were consistently low, around 0.20 to 0.27 for every model family.
Wow. So that suggests the test itself, the questions we're using to measure social reasoning, are maybe just inherently flawed.
That's the strong implication. And it points to this big trade-off they found. It's really hard to find a benchmark that has both high discriminability and high capability alignment. They rarely seem to go together.
But the framework offers a solution here, a really practical one. Selective benchmark construction.
This is the really exciting part. They used CAD and DS to filter out all the bad, noisy questions from existing benchmarks.
And by doing that, they built these smaller, more efficient tests. They got a ranking consistency of 0.93,
Which is incredibly high.
while using only 35% of the original data.
35%. I mean, that could change the economics of model development overnight.
It really could. The takeaway seems to be that high-quality benchmarks need a careful balance.
Yeah.
You can't just throw a million questions at a model.
No, you can't. Developers should be aiming for a DS above 0.2 and, more importantly, a CAD above 0.6. Those should be the new minimums for quality.
Absolutely. And that leads to our final thought for you to chew on. If we can get the same or even better evaluation quality from just a third of the data, what does that imply for the speed and the cost of building the next generation of truly massive language models?